Okay, this is video, whoops, I can't spell, 7.1, graphing exponential functions. All right, so you should have your video notes with you on 7.1 and 7.1 in your book. Okay, so in this chapter, we're going to learn how to graph exponential functions with an exponential growth factor and exponential decay factor. Let's look at our vocabulary. What's an exponential function? It's a function where the base is a constant and the exponent is the independent variable. Example, y equals 10 to the x. Remember, we have to learn and remember what bases are. So if I have y equals 10 to the x power, remember it's an exponent. So this is my base and this is my exponent, or we can call it power. When this is the variable and this is a constant, then we have an exponential function. Okay, so let's look at those. Oops. All right, so let's look at an exponential function. So the parent function is f of x, or y, equals b to the x, where b is greater than 1. Not the absolute value, just b.
I don't know that one.
The type of graph, it's a continuous and it's 1 to 1, and it's increasing. Do you see where it's increasing right here? The domain is going to be all real numbers, and the range is all positive real numbers, or another way of saying it is y greater than or equal to, y greater than 0. Okay? Because remember, 0 is neither positive nor negative. And there is an asymptote. That is the x-axis, or more specifically, y equals 0 is the axis of symmetry. It's the x-axis. And it intercepts, the y-intercept is 0, 1. And these are important to learn. Memorize these 3 points, 0, 1, 1, b, and negative 1, 1 over b. These are the 3 points that you'll always graph, and you'll make those transformations to those points if you're trying to find exact points. These are really easy points to use when you're making a table. I know the book uses a little bit, but we're going to use a shortcut and say we don't need quite as many. So let's look at example 1. They say graph y equals 3 dx. State the domain and range. So they made a table of values, and then they plotted each and sketched the graph. So they use -3, -2, -1/2, 0, 1 2/3, and 2 as our x values. They put those into the graph and solve for y and got the following values, 1 over 27, so on and so on. And then they simply graph it. So it stays the same. It didn't shift up, and the domain is still all real numbers, and the range is still all positive real numbers of y greater than 0. Now let's go back for a second. Let's talk about asymptotes. We started to talk about what an asymptote is, one of our vocabularies. An asymptote is a line. The graph of an exponential function has an asymptote, which is a line that the graph of the function approaches but never touches. So do you see over here? It's hard to tell. It looks like it's on top of it, the x-axis, but in theory, it actually approaches the x-axis, or y equals 0, but it never hits it. It goes on forever and ever and just gets smaller and smaller and smaller. Now, this is an exponential growth because that's when b is greater than 1. Okay, so the exponential parent function is f of x equal b to the x. That's an exponential function, but an exponential growth function is when b is greater than 1. All right? Now, just like in square roots, quadratics, other things we do, we can transform these. We still use this form, f of x equal a times b to the x minus h plus k. And they still mean the same thing. H and k are translations. H is the horizontal translation, right or left. K is the vertical, up or down. And a is orientation or shape. And we said a also tells us the dilation or reflection. Does it dilate and does it reflect? All right, so the absolute value of A is greater than 1, then it's stretched vertically, and the absolute value is between 0 and 1, it's compressed vertically. If A is negative, then we have a reflection over the x-axis. Now it's important to know that 3 times 2 to the x power cannot be simplified to 6 to the x power. Why? Because this is 3 to the 1. Remember our rules for multiplying exponents. You have to have the same base. And our exponents are 1 and x. That doesn't matter. But look, our base is 3 and 2. They're not the same, so we can't use the product rule. So these do not equal 6 to the x. That's really important thing to know and understand. Why? Using exponent rules. Okay, it's not any new property or new rule. It's just something we've already learned. And again, when you're learning these, learn -1, 1 over b, 0, 1, and 1, b. These are important coordinates because if you can get these coordinates, then you can make the transformation to those coordinates and get the new coordinates when you're doing transformations if you don't know them, and then you can plot them. So let's look at example 2a. It says y equals 2 to the x plus 1. They want us to graph the function, state the domain, and range. Well, I can start off with some points. I can put -3, -2, -1, 0, 1, 2, 3. Well, I'm going to put the original problem. So I'm going to do 0, 1, right? And then I'm going to do -1, and then 1 over b. What is b? b is 2. So 1 over 2. Then I'm going to do 1 and b, which is 2. So what's happening here? The only thing that I have going on is it shifted down 1 unit, which means y minus. So my new coordinates, we learned how to do this with square roots. So these are not going to change, but these are. So we're going to do 1 minus 1 is 0. 1/2 minus 1 is -1/2. 2 minus 1 is 1. So now I can go graph these, 0, 0, -1, -1/2, and 1, 1. And you see our asymptote before was y equals 0. It went down 1, so 0 minus 1, our new asymptote is y equals -1. So remember, it's going to approach -1 and never touch it. And that's how we would graph it. The domain is still all real numbers, and the range is y greater than -1. It's not equal to because it never touches. Let's look at this next one. Y equal -1/2 times 5 to the x minus 2. Well, I can identify the transformations. I can say A equals -1/2, B equals 5, H equals T, and K equals 0 because there is no vertical. There's no plus or minus out here. So we can take our 0, 1, our -1, and B is 5, so it's 1 over 5, and 1, 5. This is x, and this is y. So now I can go 0, 1, because it didn't go up any. My asymptote is still going to be y equals 0. -1, 1/5 is going to be right here. And 1, 5 is going to be up here. And now I've graphed it. And this is really all I'm requiring you to do. Know 0, 1, -1, 1 over b, and 1, b. All right, so that's what happened. The graph went to the right 2 units. Whoopsie. I somehow messed up. I didn't apply, that's the original. I didn't apply the transformation, so it's x plus 2. So x plus 2, if I put 1 plus 2, this becomes 3. this becomes positive 1. So I actually have this wrong here. So it's 1/5, and then 1, 2, 3, 5. So that is the transform graph, not this. All right. Or I could take 0, 1, say it moved to the right 2 units, which if I did this right, it does. It moves right here. But it also reflects. So let's redo this one. So we said y equals -1/2 times 5 to the x minus 2. So this is 0, 1. It goes to the right 1, 2, and it reflects. So it's going to do, whoopsie. So it's going to do this. This, because it's going to reflect vertically over the x-axis. Because originally it did this, so when you reflect it down vertically, it's going to shift and it's going to go this direction. Okay, so you can remake your points, and I just did them wrong. So, but you should get 2, -1/2, 3, -5/2, and 1, -1/10. So these are your new x, y coordinates after the transformations, and you can plot those 3 points. All right. So this is a growth because it's increasing. Now we're going to talk about decay functions. So we still have f of x equals b dx. Now the only difference is b is between 0 and 1. It's still continuous. It's still 1-to-1. So we'll go to the next page. It's still continuous. It's a 1-to-1. The domain is all positive. Asymptote is still the x-axis. The intercept is still 0, 1. Except for now, these coordinates are different. The 1, b is here, and this is -1, 1 over b. It's still the same thing. It's still the same -1, 1 over b and 1, b. This is called exponential decay because it's decreasing. It's the only difference. Now, really quick, a growth factor. If we know that, let's look at this model here, this formula. This is exponential growth with a constant % increase over a specific time. So this is obviously an accounting or a financial piece for interest. So the 1 + 4 is called the growth factor. And in this compound interest formula is A of t equals A times 1 + r raised to the t, where A is your principal amount that you started with, r is your rate of increase, and then t is the time period that it is being put in the bank and earning interest. Okay, so notice the base is 1 + r. All right, so let's move on. So the graphs of the decay can be transformed just like the graphs of the growth. Do the same thing. So y equals 1/3 to the x. So they pick some values, they put them in for x, and get these new values, and then they graph them. Okay, so here the base is 1/3. And we know it's a decay because b is between 0 and 1. So we know it's going to go down. All right, let's look at this one. This one's transform. So A is 2, so it tells you it's a vertical stretch by 2. 1/4 tells you it's a decay. H is -2 because it shifts to the left 2 and it shifts down 3. So we take this and we go, oh, here it is here, the original one. So we take it to the left 2 and we go down 3. That means our new asymptote is y equals -3. All right, it's vertically stretched by 2, so it gets closer to the y, and then we can graph our graph. The domain is still all real numbers, and the range is still y is greater than -3. All right, so let's look at these two. So you had a vertical reflection over the x-axis, so it flips over. And we had a vertical stretch by 3. We had a shift to the right 4 and up 2. All right, so and you notice that the base of a decay factor, when we're talking about compound interest, it's 1 minus r. That's called the decay factor. That same formula. All right. So do the problems and we'll see you in class.